I'm Steve Hoover. I just wanted to quickly set context for this recording and give the students a chance to talk about their projects. You'll hear from 4 students participating this summer in Google Summer of Code under the free and open source Silicon Foundation, working on projects all related to transaction level Verilog in some way. Transaction level Verilog is very central to my startup, Redwood EDA. So I've been playing kind of an oversight role, coordinating efforts across the project, and it's been really fun to get all the projects working together and the students collaborating. I'm really excited. I can't tell you how excited about the 4 projects we have going on this summer. They all have very significant ramifications for the world of open source silicon. And every week in this call, we come together and share our updates. And it's just, there's so much excitement in this call every week, seeing how quickly these projects are coming together. And we wanted to share that excitement with everybody. So we're about halfway through the summer, and I think you'll be amazed to see how far these projects have come along in just a few weeks. I'm going to ask every primary mentor to just quickly introduce themselves and introduce the project, and then each student will show what they've been working on. These are all very visual projects, so it's a good thing to demo in a video. So let's start with block-based circuit design. Gayatri, if you can introduce your project.
Sure. I'm Gayatri Mehta, faculty in electrical engineering at the University of North Texas. I'm currently mentoring this block-based circuit design project. The goal of this project is to make circuit design fun and accessible. So we would like to develop a highly intuitive tool that would help students understand fundamentals and core concepts of circuit design. So through this project, we hope to create enthusiasm among our young students about pursuing STEM careers. And I would like to thank my fellow mentors, Steve Hoover and Adam Retzman, for their contributions and support. And in this project, we are exploring how to use Blockly for circuit design. And Ninad, who's working on this, is going to demonstrate that next. Go ahead, Ninad.
Thank you, Dr. Mehta. I'm just going to share my screen. So, hello, everyone. Let us just see what is the realm of block-based circuit design. As you can see, lines of TL-Verilog code over here are represented by blocks. And these blocks are accessed by the flyout, pop-out menus on the side and can be dragged over to the workspace. Along with this, a lot of functionality has been provided for productive development of your circuits. As you can see, we can take these blocks and we can access the TL-Verilog code from it. We can also save it to our storage so that on a later date, we'll be able to come back and recover it and start our work. We can download our files and we can also upload our files and start work from there. So let us take a small example, which I had earlier created, and go through it. So as you can see, I have basically coded a validity tutorial from MakerChip, which talks about taking out the square roots of numbers. So what we can do over here is we can extract the TL-Verilog code. We can take that and we can head over to MakerChip, which is an online TL-Verilog editor, to see how the code is working. So one thing which I would like to speak about block-based circuit design is that what it provides the user is that it provides the user with all the functionalities which are available from TL-Verilog at the axis of a button click. So a lot of times when we are learning about circuit design, we are not really sure about what instructions to use. And also, one thing which it provides is that it gamifies the entire experience by being able to drag and drop the elements and seeing how your circuit is evolving from there. It makes it really fun and visual while you're designing your circuits. So I would say I'm really excited about this project and thank everyone for providing me the opportunity to work on it.
Yeah, thanks, Ninad. That was awesome. And I have to say myself, I'm really excited about this project. Like my expectations for the summer was basically to have Nanad explore what we could do with Blockly and answer questions. And we're already at that point. We already see the potential and we already have this environment where you actually can write production TL-Verilog code. There's certainly a lot more to do to massage and make things streamlined and so on. But, we've already achieved the goals of the summer of learning what Blockly was capable of providing when it comes to circuit design. So I'm really excited about that. All right, next up we have a project under Ako Shadnoiji, who's not available. I think he's on the train at the moment. So Dylan McNamee is going to represent that project, Virtual FPGA Lab. Dylan, can you introduce the project?
Yeah, so this project is designed to support teachers and students by providing a framework that lets you create FPGA designs on the screen that can then be translated into real FPGAs once the students are ready to move to that step. And I personally find it very exciting because I'm a professor and I've wanted to incorporate FPGAs in my curriculum, but the first step of getting everything installed is just kind of a no-starter. So having a web-based framework for doing this is really exciting. And the main student doing this work is Bala Dinesh, and he's got a large cast of folks helping him out. Shivani Shah and Mayank Kabra are both doing a lot of work in the background supporting this project. But Bala, why don't you show us your project so far?
So basically, this project is about showing the virtual FPGA lab, like having mimicking the same FPGA experience in a web-based backend itself. Like this part is the canvas, like where we can code this part using JavaScript. So you can see here, like we included a Z board here actually. So we can this example is about an LED. So basically, I'm using a counter for this. So we can code this canvas using JavaScript. So this part is called this. So actually, like for every cycle, I just use a counter, so you can see the LEDs are changing. It's like a counter incrementing by 1, so you can see it. And then like we support currently Z board, RTX7 board, and Basis 3 board. Yeah, so we can to change this board, you can give this. Let's say you want Basis 3 board, you can give this Z board instead of this, and give Basis 3, and you will get this. The same thing, but in Basis 3 version. So you can see here, like this is a Basis 3 board. Similarly, there is one more board called RTX7 board. So yeah, this is about LED display. So like, let me go through GitHub repository. So all the codes are uploaded here. So you can see the demo. You can just directly click on this, and you can go to the demo. So these are 4 modules I have worked so far: LED module, sound segment display, LCD, and BGA display. So yeah, I just demonstrated LED here. Let's move on to 7 segment display. So here I use again Basis 3 board. Here you can change as you like Z board or RTX7. So here I like you can also you can see here it's like a counter. So for everything count, it's like incrementing by 1. So I just enabled all the segments except the top one. So you can see here like 0 represents active and 1 represents inactive. So this one segment alone is disabled. So as we move on, it's like a counter. So let's say I want RTX7 board here. You can simply write RTX7. So currently we have 3 boards supported. We are yet to include more boards like Icebreaker and so much more boards like Nexus and so on. So yeah, we are working on that. And then the third is about LCD display. So you can see here, this is the LCD part. Like I made this, like you can see, this is the data. This corresponds to text of FPGAs are fun. So since you can see here, after cycles 30, you can see here FPGA or printing. So FPGAs are fun. You can play with this. So this is about LCD. You can see here, after 100 cycles, you will be getting a full FPGA summon. The cool thing about this part is like you can see the simulation cycle by cycle. See the visualization cycle by cycle. Let's say I'm currently 100 cycle, and if I want to go backwards, So you can just simply type 20 and see how things are there before that. So you can just play with it and you can learn exactly like what is happening at each and every cycle. So this is really cool feature in this part. And then running on to an actual FPGA, like we have uploaded the instructions for this. So we'll be using Sandpiper tool. So this is a code generator that converts TLV to either Verilog or system Verilog. So these are the steps to run. You just clone this repository and you just can run this. So you can see here, like I already did this. Yeah, so I just already run this command. So it will be asking which file you want to upload. You just give appropriate file and board name, and it will just compile everything, and ticket script will generate, and everything will be programmed in Vivado. So till generating bitstream and running into an actual hardware, it will be working. So you can see in my like I will show the output in my video. So you can see here, like it's like LED is like counting by 1. So you can see this actually. So you can our TLV code is synthesizable. So using the Sandpaper, you can convert to Verilog, and you can get the generated output demo in the FPGA, actual FPGA. So it's like it will be very useful for learning purpose. It will be easy, like you don't have to wait for synthesis and bitstream timings and all. Like for simple getting into beginners, it will be very useful to have this. Yeah, that's all.
Yeah, thanks, Bala and Dylan. That's awesome. And I also want to point out, this effort from Bala, and also to give credit to Mayank Kabra and Shivani Shah for helping out with this one as well. This framework for virtual FPGA labs is being adopted by the open source FPGA Foundation. We're working on trainings with them to disseminate this learning platform to the world. So you can see the impact that these summer of code projects are having on the ecosystem, silicon ecosystem. Next up, we have a project around tensor core development, and Theo Ontzig is going to introduce us to that one.
Thanks, Steve. My name is Theodore Omtzigt. I'm the founder of Stillwater Supercomputing, where we're working on the design and implementation of embedded intelligent systems. The Google Summer of Code project that we presented is Warp 5 tensor core extension for deep learning. That is an experiment to add tensor algebra acceleration to RISC-V systems to accelerate deep learning applications that run on embedded RISC-V systems. The secondary mentor on this project is Akoj Hadnagi, and the principal researcher of this project is Nitin Mishra. And Nitin will now provide a quick introduction to the project. Nitin?
Hi, everyone. So we are trying to design a tensor core vector processor which can be added to a sequential core. Over the past few years, there have been a lot of interest in deep learning applications. And since all of them are memory and compute bound, there have been a lot of different architectures that have been proposed. 2 of such architectures can be seen here. One is Google's TPU, and another is a standard ASIC design, which can use this inherent data level parallelism. A third approach is what we are working on, which is a vector coprocessor. And this is the high level overview of our design. So we have a scalar sequential core. It could be a Warp 5 or any other scalar core. And whenever it sees an instruction that has a opportunity to have like a vector engine, or like to work on multiple data elements in the SIMD fashion, it basically transfers that to a decoupled vector coprocessor through this instruction queue. And then this controller will basically transfer that to the vector register file, through which it will go to the appropriate functional unit. So this is the overview of our design. We are working on a single lane, single functional unit implementation. Obviously, the design can be extended to multiple lanes with multiple functional units, but this is what we are working on right now. So we have a vector register file, which is basically a multi-banked SRAM design, which can hold 32 vector registers of 32 elements each. And right now we have a single vector functional unit, and this controller will basically pass the operands from the register file to the functional unit and then back to the vector register file. So this is the coprocessor, and this is our design. We are using all open source tools, and we are using an open source ISA, which is the RISC-V ISA. The tools which we are using to build this are TL-Verilog, and which is less verbose and faster to develop. And we are using MakerChip platform to basically simulate and do a step-by-step visualization of our design. The major goals of our project is to basically be able to support 4 major instructions, which are load, store, scale, dot product, and fuse dot product. The way we differ from other designs is that we are focusing on the smaller dot product operation, and then we can augment it and reproduce it to learn the timing and resource utilization. And then all other gem instructions, which are the core of deep learning, can basically be combination of multiple of these fused dot products into a single step. So once we are done with this design, once we have verified the design, we plan to integrate it with a RISC-V core sequential pipeline, which could be warp5 or could be any other design as well. And then we want to prototype it on an FPGA board and see, optimize the design to see the timing, power, and area requirements. This is what our goal is. And then just to point out that there have been various other interests in academia on such designs. These are two different designs. One of them has already been made. On the left, you can see the ARA processor, which is a kind of based on RISC-V. And then there's an announcement of an Core 5 VEC project by Open Hardware Group. And then industry is also currently working on this vector coprocessor approach. And there are two such designs, as you can see here. On the left, you can see an S6 Aurora NEC processor, and then there is a processor by Andes design. As far as our progress is concerned, we have been able to design and verify the multi-banked SRAM. We have been able to design the decoder, which is based on the latest version 0.10 spec of the instruction encoding document by the RISC-V Foundation. And right now we are working on the sequential controller. And also a big shout out to Shivani and Mayank, which are helping me along the way to make this project come to fruition. Thank you.
That's great, Nitin. And thanks for overachieving with the slide set. That was great. So yeah, I mean, it's really exciting for me in particular to see projects like this being developed with the tools that I'm working on myself. So last project we have is from Vineet Jain, who's working on Warp5 many-core implementation as an accelerator in the cloud. And Shivam is mentoring that project, Shivam Patwar. So Shivam, do you want to introduce the project?
Sure. Thanks, Steve. Thanks everyone for describing about your projects. It's really nice to, when we are the last, then it sort of feels like, wow, all these projects were so great. Then can we justify our role here? So yeah. So to start, Warp5 is probably one of the very first TL-Verilog projects that was started by Steve. Warp5 is essentially a CPU core, but much more than what you would see in a general CPU core. It is configurable. It can support multiple ISAs. It can support multiple architecture parameters, and all that can be done with with minimal effort. And it's not like you have to recompile your code every time, or you have to write complex generate statements and so on. All thanks to the flexibility of TL-Verilog. And this time around, we have Vineet who's working on Warp5 many-core, and now the goal is that we take this very flexible Warp5 microarchitecture and extend it to support multiple cores. And then we have various applications where we can use it for teaching, learning. We can use it for generating accelerators on the web and so on. And I think I'll give this opportunity to Vineet to continue and just give us a brief overview of what all we have been playing with. Thank you.
Yeah, thanks, Shivam, for introducing. So as Shivam discussed that the Warp5 was the initial project for the TL-Verilog, and soon as we go through the journey, now we have our own configurator. So like recently also Steve he introduced for the Warp5 configurator. So this is the Warp5 configurator, and you can customize your logic and it can generate which core you want. So it has multiple configuration options. So whether you want RISC-V ISA or you want another ISAs, it can also support multiple custom ISAs and also their extensions as well. So for example, for the RISC-V, there are multiple extensions like E extension, M extension, F extension, B extension, and soon there will be more. And there's also support for multi-core. So multi-core is just like many core. So as you see, if you change the amount of code greater than 1, it can have the code can be configurable with that part also. So these are a bunch of configurable options, and we can play around with them, and it can generate the corresponding TL-Verilog code and the corresponding code itself. So we can see the diagram, and this Warp5.org configuration is basically a bunch of macros, and it's a macro instantiations, and it defines some macros, and basically those goes down to the main TL-Verilog, the Warp5 project, and this whole like is configured with a certain set of configurations, and we can see it in the maker chip. So we can see that this is the single verb5 core, the single cycle one, and this its visualization and its logic. And in the NavTL, we can see its expansion as seen by the sandpiper. And this is also its waveform. So we can jump around the signals. So one cool aspect of this maker chip ID is is the visualization feature. Sorry. So this is the visualization for the verb5 main core, and we can see that for the single core verb5 based coming from the core configurator, and we can see from cycle number 14 and so on the visualization is working. So as soon as the instruction progress through the instruction memory, we can see the particular instructions being executed, and at the same time the corresponding register file and the data memory is getting updated. So coming to the next part. So this is the insertion link. So basically for the many core, as we have many cores, so there must be a communication protocol between them. So this is the communication hardware or the insertion link. So one of the port of the core is attached to this part, and the output of the is attached to this part. So the packets will be coming in from this side, and the packets will be going to the core from this side. So this is just like connecting between two multiple cores, and this is the complete ring architecture. So this is the insertion ring architecture, and the part of the project was to debug that and to make the visualization for it. So we can see from like cycle number 21, the packets are coming from the from the core 1 and core 2 at the same time. And since it's a ping, so it's a head one. And similarly, the next packet is coming in and going through the storing through the entries of the file post, and so on. So based upon the assembly program which we give to the core, the program is working accordingly. And based on that, if we can see if any of the packet is not behaving at it should behave, then there's a bug, and we can track down through the visualization and then through the waveforms and through the logic where the things are breaking up. Okay, so the next part is basically to port this. So the part of the project was to take this whole many core architecture into the cloud. So this is the first class GitHub repo, and this is the framework in which one can communicate with the server, with the cloud applications. All we need to do is just need to code up the green parts. So basically in this case, I just need to have the custom kernel in, and there is a simple web client. Through the web client, one can access the particular the custom kernel, and the custom kernel through the streaming interface, it will give back the result to the client. So it can support like work for the different purposes, and one is the acceleration over the cloud, and the part of this project was also to port this many core on the cloud. So basically having the many core TLV inside this custom kernel. So yeah, so that's the part of my project. I would like to thank Steve and Shivam for supporting, and yeah, thank you.
Yeah, thanks, Vineet. Vineet and Shivam actually were involved in Google Summer of Code last year as well, working on aspects of Warp 5. And the contributions that they've made this summer and last summer have really helped to mature Warp 5, and now as a mini core, and now starting to integrate with this first-class framework for building accelerators using the cloud FPGAs, really opening up new models of computation to the world of open source. So it's really exciting to have their involvement on these efforts. I think you can see from all these projects how significant the work is that these students are doing over the summer. I want to thank everybody who's been involved. Their work is all freely available in open source repositories. Certainly by the end of the summer, bounce this video around social media and whatnot, and keep an eye on things because they're evolving fast. So thanks everybody. Thanks all the students and mentors for their participation and for helping put this recording together. Thanks everybody.